Hello everybody. Today we will continue the aromatic electrophilic substitution reactions. So in this regard, today we will take up reactivity and the effect of substituents. So effect of substituents on the benzene ring. So when the benzene ring has a substituent, the benzene ring has a substituent, let's say Y. So when reacted by electrophiles, so where will go this electrophile, where will go? Either it can go, electrophile can go either to the ortho position or in the para position or in the meta position. Okay. So there are three possibilities when there is substituents of the benzene ring. So we now will discuss about the reactivity effect of these substituents. So I write down when a benzene ring, when a substituted benzene, when the benzene ring is substituted, when a substituted benzene undergoes an electrophilic substitution reaction. So when a substituent is present in the benzene ring and then undergoes substitution reaction, the question is that where does the new substituent under new electrophile or new substituent attach itself. That means where the new electrophile attaches is a product. So the question is the product can be either is the product of the reaction can be either of the reaction the ortho or reaction product is the ortho product or the meta isomer or the para isomer. Okay, para isomer. So we can discuss this thing in detail one by one. Okay. So I am repeating again. When benzene is substituted, then where the electrophile can go. So when the substituted benzene undergoes an electrophilic substitution, where does the new substituent attach? Is the product of the reaction an orthoisomer or meta-isomer or para-isomer? So this will be we can discuss. Okay. The substituent already attached to benzene ring determines the location of the new substituents. So here why the substituents already attached to benzene, that is why determines the location of the new substituent. Depends on the position of the electrophile meta or ortho, meta or para, depends on the substituent Y. Okay, so I'll repeating again. So the substituent already attached to benzene ring determine the location of the substituent. This is Y in our case. This is Y. Substituents already attached to benzene ring. That is in this case that is Y determines the position of determines the location or positions of the new substituent. Okay, that is the position of the electrophile substituent. Now there are two possibilities. So they can be substituent will attach directly to the either to the auto para position or in the meta position. So there are two possibilities. There are two possibilities. Is either first one that a substituent that is y will determine direct a substituent or y will direct the incoming substituent, and this incoming substituent, that is y substituent, that is E. Okay, that is E. A substituent will direct the incoming substituent either to the auto and para positions. This is the first one. Okay, then second case is that y, that is a substituent, or that the substituent, that means y will direct the incoming substituent, that is E to the meta position. Okay, to the meta position. So there are two possibilities are there, that the substituent is y will direct the incoming substituent either to the auto and para position or to the incoming substituent to the meta position. So there are two conditions. So all activating substituents like electron donating groups and the weakly deactivating halogens are auto para directors, and all substituents that are more deactivating than halogens are auto meta directors. So we can discuss this thing. There are now two possibilities. So all the activating substituents like electron donating groups will direct the incoming substituents to the auto and para positions. Okay. Say for example, we have this OCH3 electron donating group or activating substituents. So they will direct the incoming this electrophile. So in the case of this electrophilic substitution reactions, so in first case we have, so all activating substituents direct the incoming electrophile to either to the auto and para positions. So here OCH, this is electron activating group, it directs this either to the auto or to the para positions. Okay, OCH3. I am giving one examples here. So I am repeating then, all activating substituents, that is electron donating groups, direct the incoming electrophile to the auto and para position. So I can write down here. Here in the past case decision, all activating substituents, that is electron donating group, electron donating groups, all things substituent groups direct the incoming electrophile to the auto and para positions. So this is one case. Okay. So electron donating groups present in the benzene ring direct the electrophile to either to the auto and para position. See the first case. Then another second case is the weakly deactivating halogens also direct halocells, also direct the incoming electrophile to to auto and para positions. Okay, just like the electron donating groups para positions. So here hello benzenes direct this thing. For example, I am giving you an example here. For examples, this is, let's say, this bromine here, and this bromobenzene reacts with halogen chlorine in presence of aluminum chloride. So halogenation takes place at the auto and para positions. Here in the auto positions, chlorine will come to auto positions plus in the para position and para position. Okay, para position. So this is another case. The weakly deactivating halogens direct the incoming electrophile to the auto and para positions. So the third case is that, or deactivating groups. For the third case, deactivating groups direct the incoming electrophile to the meta positions. So I write down here the deactivating groups third case. Third case, the deactivating groups deactivating groups. Okay, you can strongly you can say strongly deactivating groups, strongly deactivating groups, and all moderately deactivating groups. You can say I write down here. You can combine together. Say all moderately and strongly deactivating groups. All moderately, not weakly groups are halogens. All moderately and strongly deactivating groups, groups or substituents direct the incoming electrophile to the meta position. Okay, meta position. So all you can say to them, all the electron withdrawing groups direct the incoming electrophile to the meta position. So for example, we can write, for example, so this is a electron donating group, carbonyl group is there, COCH3, and then let's say nitration HNO3 in presence of sulfuric acid. Okay, this nitration of this acetophenone with sulfuric acid, nitric acid, sulfuric acid will give this to meta position. The incoming group nitro group will come to meta position. Okay. Another one we can check for another example we can have. So nitro, another is also nitrobenzene reacts with bromination of this in presence of ferric bromide, direct this into meta position. So they are all deactivating electron withdrawing groups. So nitro and COCH3 are all deactivating, or you can say electron withdrawing groups. So you can say that all the deactivating except the weakly deactivating groups direct the incoming electrophile to the meta position. So we can write down here, summarizing that all the activating substituents, or you can say electron donating groups, substituents, and the weakly deactivating and the weakly deactivating halogens are auto and auto para directors. Okay, auto para directors. So halogens and then electron donating groups are auto and para directors, and all substituents, you can see all the and all the substituents all the substituents you can say that are morally morally deactivating are more deactivating groups than halogens, are more deactivating groups than halogens. You can see that. Then halogens are meta directors. Okay. So electron groups direct the electrophile to the meta position, and all the actively substituent means electron donating groups and weakly deactivating halogens direct the incoming electrophile to the ortho and para positions. So this is a summarizing. Okay. So now let us see how this takes place, how this substituent Y determine the positions of the incoming position of the electrophile. To understand, so I am repeating again, to understand why a substituent directs an incoming electrophile to a particular position, that is either in the ortho or para or in the meta position. So it is necessary to look at the stability of the carbocation intermediate formed in the rate determining step. So to understand why a substituent directs, an incoming electrophile to the particular position depends on the stability of the carbocation intermediate formed in the rate determining step. So the position of this, let's say Y, okay, Y depends on electrophiles. It can give either to the ortho positions E, or in the para positions. They are all same. You can say ortho and para positions, or in the meta position. You can see here, or in the meta position. Okay. So so a substituent depends on the substituents Y to direct the incoming electrophile either at the ortho, para, or in the meta positions. So it depends on that. We have to see the stability of carbocation intermediate formed in the rate determining step. So when a substituted benzene undergoes an electrophilic substitution reactions, 3 different carbocation intermediates can be formed. So here you can have 3 intermediate carbocations can be formed. Which one is most likely to be formed depends on their relative stability. So when it undergoes the reactions, comparing this relative stability, let's say suppose first one, let's say this one, when these substituents Y, it goes, you can have 3 different carbocations. Okay, so you can attack here. You see here. You can attack here. This one attack. Then we can have another carbocation. We have this Y, and then that E. Then we have the carbocation here, position of carbocation here, or you can attack the meta positions, or you can have para position also. You can have it here. Positive charge can be delocalized. This thing, this path will be delocalized. We can have attack positive charge here. Let's say in the here, then we can have positives here. The another one we can have in the case of this meta reaction, then we can have Y. Then in the case of meta reaction intermediate, then we can have, or here the position can be either attack here, positive charge here, or it can be delocalized this way, positive charge here, delocalized like this. So position of the this positive charge can be localized, or you can have this way or this way, here positive charge here, or here 3 positions. Okay, so we can have, it depends on the carbocation in the wall. So I am repeating again, if the formation of carbocation intermediates depends on their stabilities. So where the E will go, comparing the relative stabilities of the 3 carbocations allows to determine the position of the electrophile. So I am giving here 3 possibilities, either in the ortho, para, and in the meta positions. So it depends. It depends on whether the electrophile goes to the ortho positions, or para positions, or the meta position depends on the substituent Y. So if substituent Y donates electron inductively, for example, methoxy group or methyl group, then it directs the electrophile to either to the ortho and para positions. So I am writing here, if a substituent, say Y donates electrons, Y is electron donating groups, donates electrons by induction. That you can say electrons. This is you can say electron donating groups. Then donates electron inductively. You can say inductively. Then electron going group. The induced, the indicated resonance contributors are the most stable because the substituent is attached directly to the positively charged carbon, which can be stabilized, by inductive electron donation, Okay, so I'll give example here. So that is, the carbon should be for example, let's say these groups, electron donating groups or CH3, then let's say this can have 3 positive charge electrons attack with the electrophiles, and we can have ortho positions. In the ortho position we can have 3 resonance structures or CH3, this electrophile here, the hydrogen is okay, this attack here, so you can have a positive charge here, and then these are okay. Or you can, this is again delocalized, this can be delocalized, the positive charge can be delocalized as such, or CH3, then positive charge here, then E, the is okay, then again delocalized, so can have 3 possible structure of this one, or CH3, and then we have, so here it comes, so you can have E, and H. Have positive charge here. So what you can localize in 3 positions. So here this one is the most stable. Positive charge, positive charge attached directly to the this electron substituent, means electron donating group. This is mostly stable because the positive charge can be stabilized by inductive by the electron donating from the electron donating group. So it can be stabilized by electron donation. Another one is that this is auto. Then now this is auto. Then we can have para also, meta also. Then meta. In the position of meta we can have, okay, this is OCS3, and then we can have meta position electrophile here. Then we have positive charge should be in here. Okay, then this will be delocalized, and this will delocalize like this. So we can have, so here delocalize this way, then this way. Okay, here delocalize this one. Then we can write OCS3, then positive charge here. This will be positive. Then we can have E, H. Okay, then here. Then again, this can be delocalized. Again, positive charge. Then we can have OCS3, and then okay, positive charge here. Then E, H. Okay, here positive charge is at the position of auto and para. Okay, this is for meta positions. Then this is not stable because this can be, positive charge cannot be delocalized, means going to be stabilized by the electron donating group. Here electron donating group cannot stabilize this positive charge. Suppose in the case of para positions, we can have, say, electron or CH3. Okay, then you can see E less than. Okay, then in the case of para position we have this here, and positive charge here. Okay, can be delocalized again. This can be again delocalized. Then here positive charge will be the carbon atom next to the electron donating groups. Here positive charge will be here, delocalized here. Okay, so you can have E, H. Then this one can again delocalize here this way. Then we can have another structure. So this way, H, E, H, positive charge here. So this is most stable. Positive charge at the carbon atom next to electron donating group is most stable. So here that is why the in the case of electron donating group, becoming electrophile is directed at the auto and para position. Okay, because these two are most stable. So I'm repeating again. If a substituent donates electrons inductively, that means electron donating group is present in the benzene ring, the inductive decating resonance contributors are most stable because the substituent is attached directly to the positively carbon atom, which can be stabilized by the electron donating group. Okay, this can be stabilized. Here also can be stabilized. So here auto and para are relatively more stable. This means that any substituent that donates electron inductively is in auto para director. But in the case of meta director, the positive charge cannot be stabilized by the electron donating groups. Even the electron withdrawing group, it can have positive charge. Okay, similarly you can draw this thing in the electron withdrawing group also. You can draw. Anyway, in another way we can explain this in another way. Okay, in another way we can explain. Say for example, say in a general way we can explain this. So Y, okay. So you can have this electron donating group. If Y is a electron donating group, then we can have this Y is the electron donating groups. Then you can have this one. Y becomes positive charge, then this becomes negative charge, and this Okay, these are here, and these negative charge can be delocalized again to negative charge now at the para positions, negative charge. Then again, this can be delocalized auto positions. So this is for when Y is an electron donating groups. Okay. So this is, we can have different types of electronic structures where Y is a electron donating group. Donating groups. Okay. You can say electron donating groups. So in this case, you can say here this you can have positive charge, negative charge here, negative charge in the auto para position. Okay. So here it indicates that when Y is electron donating groups, the position at auto and para positions are electron rich. So here when I'm repeating again, when Y is an electron donating group, then auto and para positions are electron rich. So the incoming electrophile can attack either to the auto positions or at the para position. That is why when Y is an electron donating group, then they directs the incoming electrophile. The incoming electrophile that is electron deficient attached to the direct to the auto and para position, because auto and para positions are electron rich. Similarly, you can have, suppose we have another one. Okay, if Y is an electron withdrawing group, suppose Y is an electron withdrawing group. So let's say Z. It is better. Another one can be substituent Z electron withdrawing groups. Then we can have another one, electron withdrawing groups. Suppose here Z, then it is electron withdrawing groups. Then we have here will be positive charge, negative charge here. Okay, then this can be delocalized. This again delocalized to this positive charge, delocalized. So Z negative charge, and this here positive charge here delocalized. Again, they can be delocalized back. This we have three resonance structures in Z. So we have negative charge, positive charge here. Okay, so three positions we have. Then this can be delocalized back to this thing. Okay, this can be delocalized to back thing. Okay. So here in this case, electron withdrawing for where Z is electron withdrawing group, where Z is electron withdrawing groups. Withdrawing groups. Okay. This electron withdrawing group. Z is electron withdrawing groups. And then we have that auto and para positions are electron deficient. So here auto positions and para positions are electron deficient. So the electrophile, another electron deficient group, cannot attack to the auto position because here is electron deficient, and the para position also here electron deficient positive charge. So this way, another way for explaining the reactivity, we can say like that. So for example, say here I will give one example for electron withdrawing groups. Say like, so let's say nitro groups. Okay, let's say nitro groups, electron donating groups, nitro groups, and okay, this is a negative charge, this is positive charge. Okay, so we can have, this can be written as like this, nitro groups can have and O negative charge, O negative charge, then another positive charge, which is a positive charge, and then this one. Okay, this can be, so when nitro groups is here, then we have these resonance structures, and then delocalize this positive charge here, then again this localize this positive charge, then we get another structures, this N positive and or negative, positive or negatives, and then we can have positive charge here. Okay, this, so two positives and two negatives. So this is for electron withdrawing groups. So ortho and para positions are electron deficient. So another electron deficient group such as electrophile cannot attack to either to the ortho and para position. So in this way we can explain. This is another way for explaining the this thing, for explaining the reactivity effect of substituents. So now this is about all about reactivity and effect of substituents. The only deactivating substance that are ortho-para directors are halogens. So another one is that only deactivating substituents that are ortho-para directors are halogens, which are weakest of the deactivators. So you should remember this thing. Okay, halogens are weakly deactivating groups, so they direct the substituents electrophile to the ortho and para. So they are also ortho-para directors. Now, summarizing some examples, I will give some examples about the reactions. Okay, suppose say some examples like sulfonic groups are present, SO3. Okay, another some examples. I will read some related ones. Reacts with this alkyl groups, alkyl halide, aluminum chloride in presence of aluminum chloride. No reaction. So here no reaction when sulfonic groups are present, or nitro groups, acylation of nitro groups, NO2, acylation CH3, COCl in the presence of aluminum chloride. Here also no reactions, no reaction. And then amino groups, electron donating, another electron donating groups. So here alkyl halide reacts with, or you can say alkyl halide, or you can say acyl group CH3, the Friedel-Crafts alkylations in the presence of aluminum chloride. So we are discussing the Friedel-Crafts alkylation, acylation when there are substituents. So here these three are no reactions are here, no reaction. Why? So it is so reaction of this sulfonic group and the nitro groups present in the amino group with the acyl. The two Friedel-Crafts reactions, acylation and alkylation of the electrophilic substitution reactions, are the most sluggish, means no reactions. So if there is a meta or on the ring, meta director on the ring will be two in an unreactive two. Meta director, if there is another meta director, then will be reaction will be undergo. So I am repeating that the two Friedel-Crafts reactions, acylation and alkylation of the electrophilic substitution reactions, are the most sluggish. Therefore, there is a meta director. If there is a meta director on the ring, the ring will be too unreactive to undergo. That's why reaction doesn't go. Aniline and unsubstituted anilines also cannot undergo Friedel-Crafts reactions here, and aniline also they cannot undergo Friedel-Crafts reaction. The lone pair electrons on the amino group will complex with the Lewis acid, aluminum chloride needed to catalyze the reaction. So this new they will form complex with aluminum chloride. So they cannot undergo reactions. So here they undergo this once they form the complex with the Lewis acid. The complexation converts an NH2 substituent into a deactivating meta director. So that's why the Friedel-Crafts reaction do not occur on benzene ring containing the meta directing substituents. So meta directing substituents are present in the benzene ring, then the Friedel-Crafts reactions does not take place. Okay. Anyway, we can, for example, I will give some examples. Example how you can go this thing. Another examples. Okay. Suppose we have this electron donating groups reacts with Friedel-Crafts chlorination. This is not this chlorination takes place to give in the para positions. So let's say para position, and then oxidation KMnO4 oxidation in presence of acid, oxidation and heat. Okay, then we'll get that this will be oxidized, methyl groups will be oxidized to acid. Okay, this is very difficult to get the orthochlorobenzoic acid and parachlorobenzoic acid. In the case, similarly, in the case of, say, you got para position, now it is suppose you take this oxidation pass, sodium potassium dichromate, okay, oxidation in presence of acid, heat, okay, this is heating, oxidation, okay. Oxidation of this pass is converted to acid, this is converted to oxidized to methyl group, oxidized to carboxylic groups, and then react with ferric chloride, chlorination takes place. So here in this case we got acid, then acid is a electron withdrawing group, so it is a meta director, okay, like this. So you can say, you can compare this to how you can prepare parachlorobenzoic acid or metachlorobenzoic acid. So I am giving one examples how can you prepare first, okay, from the electron donating groups. Okay, so here the electron donating group is mostly here auto para director. They are forming fast from the auto para director. Okay, but finally we got this acid. How you got this auto of chlorobenzoic acid, parachlorobenzoic acid, and metachlorobenzoic acid depends on this action. I am giving some examples. Okay, similarly, stability of the carbocations depends on the also forms in the alkylation reactions. Stability of carbocations. Say for example, alkylation of this stability of carbocation is more important for considering the final product. Say for reaction of this CH3, CH2, let's say CH2 with 10 chloride, so aluminum chloride at 0 degrees Celsius, chlorination of this one. So it can give either in the two position we can have CH3, then CH2, CH3. This is nearly 68%. Okay, another one is another substituent is CH2, these three are there. You can write CH2, 2, then 1, 3. Okay, 1, 2, 3. Okay, and this is 35%. So one change, this one, positive charge. Okay, so this depends on the formation of carbocation. So here carbocation intermediate can form either here. This is positive charge. He lost this one. The chloride is lost. Then we can have primary. Primary will take to this one, and this again rearrangement takes place. We got a secondary carbocation. Then we got this one. So second carbocation reacts with this one. So we got this product. Okay, so secondary carbocation is more stable than, that's why we got a major product here. So another example, say this one benzene reacts with this CH3, CH2Cl. So it gives only one product, aluminum chloride, chlorination reactions. So it reacts with these are Hadel-Crafts alkylation reactions. So here you get only one product, yield is very high. So you can have CH3, and CH2, this CH3, this CH3. This is 100%. Okay, only one product. So how it forms, because once this goes primary carbocation form, then this is not. This is also again destabilized by migration to give the more stable carbocation. This is tertiary carbocation. So tertiary carbocation reacts with way. So I want to say that the Hadel-Crafts alkylation also can take place to give the product which is where coming from the most stable carbocation. Okay, so we can have this thing. So now we wind up for all this thing for aromatic electrophilic substitution reactions. So these are, today we discuss about the reactivity and effect of substituents. So I am repeating, if the substituents in benzene ring is electron donating group, then the incoming electrophile will be directed to either to the auto and para positions. Again, and if the electron withdrawing group is present in the receiving, then the incoming electrophile will go to the meta position. So this is how this takes place. It depends on the position of the positive charge. So I have given to this in two ways of the mechanism of the reactions. So today we wind up here. Okay.